So yeah, I'm LShoneveld. I'm a research scientist here at CSIRO in Australia. And over the last 5 years or so, my colleagues and I have been looking at samples from the Norilsk deposit in northern Siberia. And I'm here today to talk to you about the platinum group minerals in the low sulfur regions of the Norilsk deposits. So this is a picture of Norilsk, the city, which is one of the northernmost cities in the world and is in the continual permafrost zone. So it's quite small, very cold, but very famous for the world's largest single resource of nickel, copper, and platinum group elements in the world. So this is Norilsk 1, which is a big open pit mine now, where we're mining out the globular sulfide ores, which you can see an image of up in the top corner. So the Norilsk Talnak deposits are associated with the Siberian Traps Large Igneous Province, which was a massive outpouring of basaltic magma that occurred during the Permian-Triassic transition. This massive outpouring of basaltic magma covers about 7 million square kilometers of the Russian land surface. And to put that in a bit of perspective, the entire Australian land surface is only 7.6 million kilometers. So we're looking at a very, very small ore resource compared to the very, very large basaltic landmass that was extruded. So this is a nice cross-sectional diagram of each of the deposits that was published by Yao and Mongol in 2021. And you can see that the Karalak intrusion is quite long and thin with massive sulfides on the bottom, globular ores on top. Talnak is quite small and sits on the other side of the Norilsk-Karalak fault. And then we have the Norilsk 1 ore body, which I showed you in that image just before. So you can see the open pit cut in there, and we're mining out the globular ores. And you can see that Norilsk 1 doesn't have that massive sulfide section at the bottom. So this is a schematic cross-section of each of the ore bodies. So at the base of Karalak and Talnak, we have massive sulfide accumulations, which you can see in the image just to the side there. And then we have these globular ores. So the globular ores are subspherical accumulations of sulfide, which are differentiated into chalcopyrite on top, pentlandite and pyrrhotite on the bottom. And these are hosted in what's known as a taxitic gabbrodolerite. So taxite in this case is referring to variable textures of the silicate mineralogy, as well as some xenolithic fragments in these samples as well. The globular ores also continue up in the stratigraphy to the picritic gabbrodolerites. So these sections don't have as many of those xenolithic fragments. The grain size is a little bit more consistent and they have a little bit more plagioclase in these samples. In these samples, you can also see the globules are a little bit flattened and elongated, which is a really good indication of which way is up in these samples. And these samples also have a silicate cap associated with the sulfide. So I've highlighted it in this image, which comes from Steve's publication in 2019, all about droplet bubble pairs. And you can see that each of these little sulfide droplets has a small silicate cap on the top of each of these droplets. So we used a lot of X-ray fluorescent mapping in this study. So this is an image from the Australian synchrotron, where we're measuring relative concentrations of elements and then creating these false color images. So you can see there's a cross-polarized thin section image on top, and then we're looking at the exact same thing just in chemistries from the synchrotron. So what we can do is use these images to look at the texture and the chemistry, and then we can infer mineralogy as well from these large images. We can also scan quite large areas to look for quite rare phases, which will come in handy when we start searching for our platinum group minerals. So in this sample, we're looking at a chrome iron calcium map. So you can see that the olivine, this is a nice skeletal olivine, shows up in these dark green colors. The sulfide is very, very bright green. You can see these vesicles, which are the relic bubbles in the silicate framework that are associated with the sulfide globules. There's another one just there. Then we have clinopyroxene, which shows up as pinks and purples. And then we have plagioclase, which shows up as the blacky blue stuff in the background. So we did a whole study looking at these zoned pyroxenes, which look like they are quite common in a lot of magmatic sulfide deposits. So you can see they zone from chromium rich in the cores out to chromium poor at the rims. These clinopyroxenes are also the things that probably grew for the longest in the system, because you can see that they start to intrude inside these sulfide globules while the olivine framework sort of stays along the outside of the sulfide globule. And then most of the images I show you are going to be chromium iron calcium combinations. But if we change up the color combinations of the X-ray fluorescent maps, we can look at a whole bunch of different phases. So this is focusing on the sulfide. So it's the same sample, just focusing on the sulfide chemistries. So you can see that it's highlighted the chalcopyrite in teal, the pentlandite in pink, and the pyrrhotite in blue by using a nickel, copper, iron combination. So as well as X-ray fluorescent mapping, we also did analyze a few of these samples using computed tomography or micro CT. So we just got a little slab of rock and scanned it with some X-rays to get a 3D volume of the rock. So this is the same sample scanned in the micro CT. Then we cut a thin section of it and then scanned it with the X-ray fluorescence. So not only can we analyze what's going on in 3 dimensions, as well as searching for those platinum group elements in 3 dimensions in the micro CT, we can also use the micro CT to target areas that have features of interest. So in this case, we wanted to target the bubble that's associated with the sulfide. So you can see there's a nice sulfide globule down the bottom, and then there's a nice silicate cap, which is interpreted as a relic bubble that's been infilled with very, very late stage, highly fractionated silicate melt. So this association of sulfide and bubbles has been shown experimentally a number of times. There was the publication that came out this week that shows some analog modeling of sulfide and fluid. This is experimental work that's showing the association of sulfide and fluid bubbles. And then Jim Mongol in 2015 showed the very, very high affinity of sulfide globules with vapor bubbles. And then it's thought if you have the correct ratio of vapor to sulfide, so quite a bit of vapor, a little bit of sulfide, you can actually raft these sulfides like a hot air balloon. So you get enough vapor to overcome gravity, and the affinity of sulfide to the vapor is so strong that it actually pulls the sulfide up with it as it rises through the magma chamber. This can also help with some of the coalescence of some sulfide globules, as you can see in this little animation on the screen. But we're interested in platinum group elements. So what we did was take these samples from Norilsk and scan them using X-ray fluorescent technologies and look for platinum hotspots. So this is some samples that were scanned using X-ray fluorescence on the synchrotron. And it is an iron shown in blue and then platinum shown in yellow. So just two colors here. And you can see that the platinum group elements are associated with the edge of this sulfide globule. So they sit just at this little border between the sulfide and the bubble. Looking at another sample, we have this nice spherical globule from Norilsk 1, and we've highlighted all of the platinum hotspots with a little yellow circle. So you can see that a lot of the platinum minerals all sit along the edge of this globule, and then a few of them sit in these late pyrrhotite veining. A few of these platinum group minerals are quite large as well. You can see this one is 0.2 millimeters about across. So they can get quite large in the Norilsk 1 ore bodies. So we scanned a whole bunch of samples, looked for anything that was a platinum hotspot, and then using GeoPXE, we can sum the spectra, the neighborhood pixels around each of these hotspots, which lets us know what phase the platinum group minerals are sitting next to. So we're going to do this to find out what these platinum group minerals are associated with in these samples. So in Norilsk 1, the picrogabbro-dolerite sections, we found 264 platinum hotspots, and the vast majority of them were associated with sulfide. There were quite a few mixed phases as well, so it was a bit hard to determine what was the closest, the best phase associated with the platinum group elements, but the ones that we could distinguish were mostly sulfide. So in the main globular ore section of Norilsk 1, there's a very, very strong association for the platinum group elements with the sulfide. So now moving to the low sulfide region. So the low sulfide region of Norilsk 1 occurs at the very, very top of the intrusion. So you can see the globular ores are way down here in the schematic cross section. The low sulfide PGE rich ore sits at the top. And this is what the samples look like. You can see that there are some sulfide in there, but it's quite a small proportion compared to the globular ores that we were looking at before. So we scanned this entire piece of drill core using the X-ray fluorescence Maya mapper at CSIRO, which allows us to look at the textures and chemistries in a little bit more detail. If I do another chrome, iron, calcium map, you can see that there is some chromite rimming a tube vesicle. So these have quite sharp borders along this tube vesicle, and then sort of diffuse borders into the just silicate framework. There are some sulfide in here, which shows up in bright green. And then there are these amygdales, which are interpreted as being voids, which are filled with late stage hydrothermal minerals. So using the X-ray fluorescence mapper, we can also look for where the platinum group elements sit. So this is an image showing nickel in red, platinum in green, and iron in blue. And I've highlighted all of the platinum hits in little yellow circles. So this takes our quite large piece of drill core and allows us to make thin sections in the regions where there's most likely to be platinum group elements. So we made a little thin section from that tube vesicle. So I've put a little box around here. This is where we're going to focus. And we made a thin section and took it to the Australian synchrotron. The Australian synchrotron XRF beamline allows us to get pixel sizes of about 1 micron. So we can look at very, very small platinum hits in these samples. In this example that I'm showing you here, the pixel size is about 2 microns, and I've highlighted the main platinum group element hits in little yellow circles again. So once we know where the platinum group minerals are sitting, we can take them to the SEM and do a little bit more of a detailed study. So here we're looking at a platinum group mineral which is in the center of this tube vesicle. It's associated with a chalcopyrite, and you can see it's quite a complex mix of platinum group minerals. So we have a rhodium platinum arsenide, which are these darker colors. The brighter color is a platinum arsenide, and then this main body of the mineral is a palladium tellurium arsenide. So quite a weird assortment of platinum group minerals. This next little mineral that we're looking at, it occurs at the edge of the tube vesicle. So you can see this is the chromite on the edge of the tube vesicle, and the platinum group mineral just sits just next to the chromite there. And this is mostly a palladium arsenide and a platinum iron alloy. So using the synchrotron itself, we can also look at where these platinum group elements sit. So the good thing about the synchrotron is that you get a little bit of volume and depth in your analysis. So the thin sections that we were looking at were 100 microns thick. So we're not only looking at the surface, the X-rays penetrate through the entire 100 micron thick volume. So a lot of these tiny, tiny platinum group minerals that we're looking at are actually existing below the surface, but it helps us understand where they're most commonly found in these samples. So this was scanned at 1 micron pixel resolution, and you can see the scale bar is quite small here. So these are the very, very small platinum group minerals that are existing in these chromite seams. So this is another sample now, still from the Norilsk 1 low sulfide ore. This is a chromite stringer. You can see some chalcopyrite existing amongst all the chromite. And we're looking just about here in this image, which is another chrome iron calcium X-ray map like we've been looking at before. So on the SEM, I highlighted the platinum group minerals in little circles, and looking a bit closer, they're mostly palladium-based platinum group minerals with palladium arsenides and palladium platinum iron alloys. And then looking inside this little vesicle, just here, we have a palladium tin mineral and then a rhodium platinum arsenide as well. So this is a third sample from these low sulfide ores. You can see that this one has a lot more of the bubbles in it. It has very little sulfide, but it's basically a bubble foam. So a very, very tightly packed region of spherical bubbles, all rimmed with these little chromites. So doing the same thing again, we can look where the platinum group minerals sit. And one of them sits inside the bubble here, but most of them sit within the chromite on the edges. We also scanned this same sample in 3D in the micro CT, and you can see all the bubbles are spherical in 3 dimensions as well. You can see some sulfide popping up in the very, very centers of these bubbles, and then every now and then you'll see a little bright, very, very bright flick, which is which are the platinum group minerals. We've taken a few little screen grabs here to highlight where all the platinum group minerals are sitting. So some of them are associated with the sulfides, the relic sulfides that exist in the low sulfur ore, but most of them sit within the chromites. So doing the same thing again, we scanned a whole bunch of these samples on the Australian synchrotron, some to the neighborhood pixels around each platinum hotspot, and made a determination of what mineral are most closely associated with these platinum hotspots. In these low sulfur zones, it's overwhelmingly that these platinum group minerals are associated with chromite. A few of them are associated with pyroxene, a couple are associated with some sulfide phases, but the vast majority are associated with chromite. So there's a really, really strong association of these platinum group minerals with chromite in the low sulfide ore. So to understand what's going on here, we have to understand all about Norilsk and sulfide and bubbles and chromites and PGMs. So I'll walk you through what we believe is going on to form these regions of Norilsk. So as I was covering before, if you have the right combination of vapor and sulfide, you can probably raft the sulfides up towards the roof. It's thought that maybe you could raft spinel up there as well, which would help to explain why you have so much spinel at the roof of those low sulfide ores. The amount of vapor that's saturated in the silicate magma can actually nucleate into bubbles just on the spinel surface. So the roughness of the spinel surface can actually allow for bubble nucleation to occur and allow more of these gaseous phases to nucleate and exist even when there's no sulfide around. When there is sulfide around, there's a lot of decompression occurring, so the sulfur can transfer from the sulfide into the vapor phase, which can concentrate the metals and PGEs in the sulfide, and also cause the accumulation and precipitation of platinum group minerals in the sulfide. So that might be what's occurring in the globular ores down in the main ore zone of Norilsk, the Norilsk ore bodies. But up the top of in the low sulfide ore, it's as there's such a high association of the chromite with the platinum group minerals, it's probably more likely that the main factor for crystallizing these platinum group minerals is actually a redox zone created from the crystallizing chromite itself. As it crystallizes and steals all the iron away from the little boundary layer as the chromite's crystallizing, it can actually cause PGMs to nucleate in that redox layer. So as decompression continues to occur, we start to expand all these bubbles, which can burst into little daughter bubbles as well. We're pushing all the chromite to the edges to make those nice little rims that we can see 265 million years later when we start to look at these rocks. And the continually growing and accumulating chromite is making more of these boundary layers and causing the crystallization of those platinum group minerals in the edges of those chromite. Then as everything starts to solidify and crystallize, we start to get gas filter pressing, where the gaseous bubble starts to decrease and starts to draw in all of the trapped liquids and fractionated liquids into these bubbles and start to cause that infill of the late highly fractionated silicates within these bubbles. And then basically everything becomes solidified and the sulfide starts to differentiate into chalcopyrites on top and pentlandite and pyrrhutites on the bottom. So if you wanted to, you could create your own little Norilsk deposit. So this is our Norilsk in a wine glass that we found just randomly one day on the internet. So what we have here is oil, which represents our silicate magma, sulfide, which is our water in this case. Our metals and our platinum group elements are signified by that little red drop of food coloring. And then we have our vapor phase, which is signified here with an effervescent tablet. And you can see as it starts to effervesce, it starts to mix all of the sulfides and PGEs into the magma, into the sulfide, starts to make those vapor tubes, and globules start to rise up through the silicate magma, and then they start to collect on the top. So at the top there, we have our PGEs and bubbles alone, so we don't have any of the water there. They're just basically little bubble frames with the red food coloring, so just PGEs and bubbles sitting at the top. And of course, we have some aerosols coming out of the top of this deposit as well. So if we freeze this image, you can see that it's a nice little representation of sort of what's going on stratigraphically in Norilsk. And of course, as we see all of these relic bubbles present in Norilsk, it suggests that there were very, very high vapor and gases present during the Norilsk formation and during the formation of the Siberian large igneous province. So it suggested that these nickel aerosols and vapor actually caused one of the largest mass extinctions of all time, because the Siberian large igneous province is actually happened at the same time as the Permian Triassic mass extinction, where 81% of all of marine species were wiped out and 70% of all terrestrial vertebrae were wiped out. So this is one of the largest extinction events on the planet. And it's interesting to think that our quest to understanding the Norilsk deposit to find more ore bodies is actually helping us to understand what's going on in Earth's history as well. So that's all we have time for. If anyone has any questions, feel free to reach out, whether it be via email or social media. And thank you for everyone who helped me with this presentation and collecting the data and providing the samples. Thank you.